Right, so we can start by introducing ourselves. We're from Adlai Stevenson High School team number 14485, and I'm Spandon, and I'm a junior.
I'm Andrew. I'm also a junior.
I'm Grayson. I'm also a junior.
I'm Gabriel, and I'm a junior.
And I'm Joy, and I'm also a junior.
All right, then let's begin. Hello, judges. We are team 14485 from Adlai Stevenson High School in Illinois.
In this presentation, we discuss our solution to the 2021 M3 Challenge, Defeating the Digital Divide. In part one, we used the differential equation along with the concept of market supply and demand to predict the cost of internet bandwidth over the next decade in the US and the UK. Next, in part two, we split bandwidth usage into categories and activities, and then created 90 and 99% thresholds using a Python simulation. Lastly, in part three, we devised our own ranking system to optimally distribute 5G cellular nodes, applying it to three hypothetical regions given to demonstrate the system's flexibility. Let's move on to part one, which is the cost of connectivity.
For this part of the challenge, we are tasked to model the per unit cost of bandwidth over the next 10 years. And so in part one, we utilize a differential equation to relate per unit bandwidth costs over time. Some of the key assumptions that drove our model include Assumption 1, in which we assumed a proportional relationship between people who purchase fixed broadband subscriptions and people who have internet access. For example, it's reasonable that a large city like Chicago has more people with broadband subscriptions and internet access than in more rural areas.
For assumption 4, we assumed an economic model of supply and demand in order to determine an equilibrium for per unit bandwidth cost. 5G networks are a commodity just like any other, and therefore can be approximated using the supply and demand model. For assumption 6, we assumed a logistic decay model could be used, which we felt was justified because of the logistic nature of internet demand. Initially, there was slow growth of internet demand, but as newer technology arrived, faster rates of new users appeared until demand leveled out at its carrying capacity.
And so per this assumption 6, the relationship between the unit cost of bandwidth over time is logistic. Therefore, according to the normal differential equation for a logistic decay curve, we constructed the formula shown here relating our cost C and time t. Here, we decomposed the normal constant of proportionality of a logistic decay into three different constants. The percent increase of supply per year S, our supply constant, the percent increase of demand per year D, our demand constant, and a final constant of proportionality K1 to fit the curve to past data.
By assumption 4, because we have assumed linear supply and demand for equilibrium, the S over D factor in our differential is motivated by the fact that the rate of cost decline decreases as demand increases, and the rate of cost decline increases as supply increases.
And so for our calculation of the annual percent growth in supply, we directly researched data on submarine cable market growth. Since the submarine cable market takes up approximately 90% of all internet supply, we felt this estimate was reasonable to account for the entire supply market. Submarine cable growth came out to be around 7.1% annually, so we approximated our supply constant in the cost-time differential equation to be around 1.071.
As for finding the value of the annual percent growth in demand, we used historical data to derive two logistic regressions. The table on the left shows the number of broadband subscriptions over time, while the table on the right shows the number of people with internet access over time. Per assumption 1, we chose to use broadband subscriptions as a measurement of internet access because of their assumed proportionality. And so after plotting both logistics based on our given data and calculating this constant proportionality, we were then able to extract our coefficient for demand D, which came out to be around 0.0803% growth annually.
And finally, after calculating our supply and demand constants, we integrated our original cost-time differential equation and arrived at our final model for the unit cost of bandwidth over time. The US model is shown here on this slide. So now, with all the unknown variables calculated, we found that the unit cost of bandwidth for the US and UK in 10 years to be around 38 cents and 54 cents respectively. For reference, the current unit cost of bandwidth in the US and UK is 43 cents and 60 cents respectively.
Even though we believe our model is robust, there are weaknesses that we need to address. Our biggest weakness is that our model relies heavily on the linear model for supply and demand. While this model may be a good approximation of the current market for internet bandwidth, ultimately this is an oversimplification of the real world. We also do not take into account the development of more efficient cable systems in the near future. Because of the increasingly pressing demand for faster internet in today's world, This cable development may cause errors at the back end of our 10-year prediction model. And finally, it may be difficult to extend our model to other countries since the equilibrium supply and demand model applies to the capitalistic-driven economies of the US and the UK.
But this also contributes directly to what makes our model robust. Our model relies chiefly on historical data to create prediction costs over the next 10 years, and based on the nature of modeling supply and demand, economic precedence gives us confidence that our model will remain accurate in the near future. In addition, because our model takes into account current supply and demand growth factors for bandwidth consumption, it is adaptable and can easily calculate updated predictions to account for any erratic changes in the market as time goes on and the supply and demand constants may change. In this way, our model is sustainable and can continue to be useful in the long term. And finally, we performed a sensitivity analysis by adjusting the variable d over s within the ranges of 5 and 10%, which ultimately led to little effect on the final bandwidth cost, further supporting the validity and robustness of our model.
Having established a model for national scale unit cost of bandwidth, now let's move on to part 2, where we focus more on bandwidth costs at the individual level.
Before we begin, we'd like to restate the problem and our motives. We wanted to first create a model to predict a household's needs over a year, then analyze each of the families given, and finally apply the model to get a 90 and 99% threshold for annual bandwidth usage.
Here are the assumptions we used for part 2. We assumed that a normal model would be able to predict bandwidth requirements through a confidence interval. This is because the day's bandwidth usage can vary as the time spent on the internet changes. Since the internet is used every day, we have a large enough sample size to use a normal distribution to create our model.
We assumed each person to be representative of a population of people in that age group. This assumption is reasonable as most people use the internet for about the same tasks. We do, however, acknowledge that the M3 graduates in the third family may be more productive than the average person of their age. We also assume that entertainment, schoolwork, and office work encompass all categories of bandwidth usage. We arbitrarily define these categories to encompass all possible usage of bandwidth throughout the day by either a student, an unemployed adult, or a full-time worker.
While many video conferencing platforms such as Google Meet and Microsoft Teams exist, Zoom is arguably the most common video conferencing platform as it is used almost universally in schools and workplaces alike.
We also assume that seasonal weather effects do not impact the usage of internet. Internet infrastructure in modern times is robust enough to not be affected by regular environmental factors. In order to tackle the problem, we started at a larger scale and worked our way down. First is the family level, since there are 3 distinct groups of people asked about in the prompt. The next logical level will be a person within a family. To fully be able to calculate all of the bandwidth usage by a given person, we decided to split up their usage of bandwidth into 3 categories: entertainment, school, and work. Of course, since each of these categories is very broad, making a bandwidth requirement calculation off of only categories would be very difficult and inaccurate. Therefore, we decided to go one level further and break up the categories into individual activities. These are the activities we considered in our model. Some activities are solid colors, while others, namely TV streaming and homework, are gradient colors. These gradients identify severe variability in these activities, which we will discuss in more detail soon. These are the equations to find bandwidth used by an entire family. The first equation finds the bandwidth used by a given person in a given internet category by summing up the product of their activity usage time, T of A, P, and their average bandwidth consumption for that given activity, mu of A. We then sum this over all categories and then over all people in a family to find the total bandwidth consumption of the family.
Going back to the activities we discussed earlier, TV streaming and homework are gradient colors because their T of A, P values vary greatly. We used a normal distribution to model this variability. While we had data providing us the mean and standard deviation of the time spent on homework, this was not the case for TV streaming, and we will discuss in the following slide as to our solution to this problem. We found data regarding the probabilities of how much time a person would spend streaming TV separated by hours. Then we made a probability mass function and put that into a Python simulation to randomly simulate the hours of TV streamed per year for 3,000 years. A visualization of that simulation progress is seen here. We approximated the results from normal distribution, and the mean and standard deviation are displayed on the right. Now we get to the second piece of the bandwidth equation, mu of A. Here are the values for mu of A for different activities shown in a bar chart on a logarithmic scale. Despite their low bandwidth usage, we considered homework and surfing in our calculations as they make up a large portion of a student's and person's internet usage outside of school. Now that we have both the stable and varying T of A, P values for everyone in the family, we can combine these values into another normal simulation, which simulates the time spent per year or per activity per day for an entire episode of length 1 year. These values then get plugged into the bandwidth equations we showed earlier to give us the total bandwidth usage for a family. This is repeated for 1,000 years as seen in the visualization. These results were approximated with the normal model, and the mean and standard deviation are displayed on the right. If multiple people performed an activity with variability, the normal models representing T of A, P were added in quadrature. Once we have the values for the normal distribution modeling the bandwidth used for a given year for that family, we can find the top 10% and top 1% of the area and see where the threshold lies for bandwidth usage. For family 1, this is 4,150 gigabytes per year and 4,153 gigabytes per year, respectively. The same process was repeated for family 2, which consisted of a grandma with her 2 school-age children who stayed with her, or grandchildren who stayed with her twice a week. The kids staying with her explained the homework time required per week. To get the results for family 2, we repeat the same process as we did for family 1. We get that 4,548 gigabytes and 4,554 gigabytes are the thresholds for 90 and 99% coverage, respectively.
Finally, for family 3, we repeated the same process we have done for families 1 and 2. Family 3 consisted of 3 former M3 students living together who are undergraduates and also work part-time. This explains the large number of hours for school, work Zoom, and also for homework. Again, the same process was applied to get results for family 3, and we get that 12,188 gigabytes and 12,191 gigabytes per year are the thresholds for 90 and 99% coverage, respectively. This is a relatively large number compared to the other families, which makes sense because of this family's high-use persons. In terms of weaknesses, our model fails to account for seasonal variation in bandwidth usage, such as kids not using Zoom as much in the summer compared with the rest of the year. Also, the model failed to account for dependencies between certain activities. For example, when a student has a lot of homework, they do not spend as much time gaming or streaming TV. Our model's biggest strength was in its ability to account for all the key factors of bandwidth consumption. The model was also able to take into account the COVID-19 pandemic by adding in the bandwidth consumption of school and work Zoom. Furthermore, the model was also able to achieve robustness because of the manner in which an individual's bandwidth consumption was broken down into categories, which were then further broken down into activities. Therefore, because of the nature of our model and procedure, we're able to apply the model to any family as long as data is given.
Now moving on to part 3 of our model, mobilizing mobile. Our general goal for this problem was to create a ranking system to rank the different subregions in order of importance for the development and implementation of 5G cellular nodes. Most of our model is based on these 3 assumptions. Firstly, that cost of living, age distribution, and smartphone usage are constant in subregions. And this is because we were not provided the subregion level data for this information. Additionally, we assumed that all cell towers have the same range and elevation that was to create a uniformity among cell towers that allowed us to better consider the geographical distribution of the towers. And lastly, we ignored the impacts of interference, and this was also assumed mostly for lack of data. Using our assumptions, we created a model to rank each subregion based on the information provided in the challenge dataset. We came up with 5 primary factors that would influence the decision of whether or not to distribute cellular nodes to a region. And for each factor, we then scaled each subregion on a range from 0 to 100, with the highest score subregion scaled to the value of 100. The first factor that we identified was adjusted income, which we found to be the median wage divided by the cost of living. And this created a standardized money system. And because of the cost of 5G, we wanted to identify those with more disposable wages to spend on commodities, such as 5G cellular networks. We also identified population density as an important factor to consider, as the more dense a population is, the more effective each individual cellular tower is. With a fixed range for each tower, the more people within the area of coverage, the more efficient. We also consider the number of towers needed to cover each area, such that the region with the least number of towers was ranked best. 2 more factors that we considered were smartphone distribution and proportion of people between 15 and 64. And this was to identify the demographics most likely to utilize 5G services. For one, only those that use cell phones can actually use the cellular networks. And likewise, children typically get their first phone at around the age of 15, while the average age of retirement is around 65. And after retirement, people are less likely to fully utilize 5G services. Another factor that would play a role in real scenarios that we didn't consider is interference, which we'll also talk more about later. So we then calculated these values for each subregion and scaled them to arrive at this table of results. The 2 largest and 2 smallest scores are highlighted to show the difference in ranking between the different subregions. So our model is slightly lacking in that we fail to consider the interdependence of the factors. For example, adjusted income and cell phone usage. Those with higher incomes are more likely to have cell phones, potentially double counting the impact of individual factors. Similarly, we were unable to recognize the different levels of impact for each factor and instead weighed each factor equally in our overall ranking. Lastly, we oversimplified the impact of interference, but this also proves our strength, which is the adaptability of our model. So given data, we could introduce an interference factor that's similarly scaled such that the region with the least interference is ranked best. And this could hypothetically be calculated by finding the area density of structures taller than 150 feet, which is the lower bound of the average height of a 5G tower, making it a safe estimate for the impact of interference. Our relative scaling also allows us to avoid encountering problems with the exact values for each region as well, which allows us to create a better comparative ranking between the different subregions. And finally, our strength comes from our ability to consider the various factors with different implications, the socioeconomics, the geography, and the demographics of each subregion. Thank you for your time, judges. Do you have any questions for us?
We do, but before that, thank you very much. Nice job.
Thank you.
Thank you. That was very nice. I've got a question about your Monte Carlo simulation. First of all, for a given family, how many times do you run, or how many samples do you take for a given simulation?
We take samples for 1,000 years and 365 days per year, so 365,000 samples per family for a day, and then 1,000 samples if you're looking at the yearly bandwidth usage.
Okay, and you assume that you're going to end up with a normal distribution, but you've got that much data. Why did you decide to use a normal distribution and not just use the quartiles from the data itself?
Well, we decided to use a normal distribution because we thought that they would add more nuance to our model, and simply because it was easy to run a simulation with the normal model and then compile all those results. And when we looked at the histograms, we saw that they were approximating a normal model. So we decided that a normal model would be the best approximation for those histograms. And then from there, we were able to find the different thresholds. So if you, for 90% usage, for 99% coverage, let's say a family wanted to have a very conservative estimate, then they could go for, or a very safe estimate rather, they could go for a very high like coverage value, like 99.99%. If a family wanted to go on the slightly lower end, like maybe 80, 85, or something like even 70%, they could do that as well. So if that's one of the advantages of using a normal model. You get that continuous ability to have any threshold that you want.
Okay, thank you.
Hi, so I'll go next. I had a question about your something that appeared in your paper that I didn't hear in your talk. In your approach for question 3, you talk about developing an importance factor or score that is between 0 and 500. I mean, can you talk about how that relates to the factors you just mentioned in your talk and how you used it to come up with your solution to question 3?
Yeah, so I think that might have been worded a little poorly, but the importance factor is just the sum of all the 5 individual factors. So that's why it would be between 0 and 500 as well.
Okay, I thought so. I just want to make sure.
Okay, so all the way back to question 1, you're using this differential equation, this logistic model. I see that you had cost and supply in that equation. And then I saw later that you said you integrated it. And so I guess my question is, did you assume that those were constants for the purposes of integration? And then at some point you were talking about them being linear models. Could you sort of elaborate on that piece?
Yeah, so generally, because we assume that the change in population over our short 10-year period would be negligible, and because we're taking all of our predictions in what we would consider to be the near future, we assumed our supply and demand constants to be constant, just for the purposes of integration. So we didn't necessarily make the supply and demand constants as functions of time, but one of our advantages of our model is that they could easily be substituted out for different constants at some point in the future to help us create more accurate predictions as time would go on.
Great. And I'll open it up to other questions.
I have a high-level question about the last problem. In coming up with the scoring function, you took into account things like median income and the number of people between the ages of 15 and 64. So it struck me that the solution to this problem was maybe tailored from the perspective of, say, an internet service provider who is trying to develop the areas where they could make the most profit off of extending 5G. Say you were asked to adjust your modeling to provide information to a municipality or a government who is trying to get internet to, say, families getting kids online for school. How would your approach to that problem have changed?
Well, I think our approach to the problem was based a lot on the idea that developing 5G services should be catered towards the people most likely to use 5G services, and that would generally be the people of like above a certain age group that can afford 5G services, because 5G is generally more expensive than other services. But in the case of like focusing towards a municipality that's looking to develop internet services or like just cellular services in general for people attending school, we could probably look at different factors as well. We could look at perhaps like we could change the way that median income would work, or like so that the areas with like the lower standardized incomes, I guess, would be developed first, because that would be the most like beneficial for the society as a whole rather than for the ISPs.
Okay, thanks.
Hi, this is Cleve Moeller from MathWorks. I'm just coming in on your paper here the last minute. This is the first time I looked at it. And I'm looking at your tables 2.6 and 2.7. I don't have any idea what these numbers mean and what the units are. Here's 2.6 it says total bandwidth in megabits, but then it's 97 million megabits. That the family 3, 97 million megabits. That isn't bandwidth. It's something else. What are those numbers in that table?
Yeah, so it is bandwidth usage, but it might seem very large because those numbers are actually in megabits, because when we did all of our calculations, most of the data that we found was in megabits instead of gigabytes, which you would normally consider. So if you divide those numbers by 8,000, you get table 2.7, which shows you the values in gigabytes for how much usage there is per year, which is why those numbers seem very large.
Still, I don't understand. 97 million megabits? That's what? That's 97 times 10 to the 12th bit? That's not bandwidth. I don't understand what those numbers are.
Well, it's just a different unit of measuring bandwidth, except the unit is just extremely small. So those numbers seem absurdly large, and they're also for a year. So if we convert those numbers into gigabytes, you do end up getting about 12,000 gigabytes for family 3, which, as we explained in our presentation, is reasonable because the people are using a lot of internet. You know, they have part-time jobs, they have school, and they have homework and other tasks as well.
I think those tables may be total number of data. It's not a bandwidth. It's total amount of data.
Yeah, so these numbers are the total bandwidth consumption over a total of 1 year. So instead of giving our bandwidth numbers in terms of megabits per second like they normally are, this is sort of summed over the entire year. So to get a megabits per second, we would have to divide by the 7 million or however many seconds there are in a year, which would probably give more like reasonable numbers.
All right, so it's not bandwidth. Well, bandwidth is something per second. Like 1 gigabit. 1 gigabit is a huge bandwidth.
I actually have a question that goes back to Professor Black's question from before. In your Monte Carlo simulations, whether or not you did a normal approximation or used empirical quartiles, how did you decide on the number of runs for those? So you said, I think you used 1,000 years and 1,000 repetitions. How did you decide on those numbers, and how did you know if that was enough or if you needed more, if you could have gone away with less?
So as you know that if we have a population, right, if the population is very skewed, you obviously want a large sample size so you can approximate it more to a normal model. And then if the population isn't skewed, maybe with a smaller sample size would work as well. So we used 1,000 because that's a pretty safe estimate. That's a very large sample size. And we thought that a sample size of 100 would be large enough so that even a skewed population would be converted into a relatively normal model. And we weren't sure, because we're just modeling the problem, right? We're not sure if the population is very skewed or if it's a relatively normal population. So we chose 1,000 because it's a pretty large number. And I think larger numbers would have slowed down our computation time, because in the 14 hours, we also had to spend time computing all of these values and running the simulation. So we thought that 1,000 was kind of like the sweet spot. So we went with that.
Okay, great.
I think that's a good lead into a question I like to ask the teams. So what was the biggest challenge for your team over that day?
I can answer that question. So in the beginning, we were trying to find data, and we were trying to, I think one of the biggest challenges was deciding what route to go for with our model, because there were multiple possibilities that we were considering for each part, and as well as trying to use the data that we researched and the data that we were given in order to create a model that optimally uses all that data and also answers the prompt in a correct way.
Any other team members want to add to that?
I think something else that was a little difficult to like work around was that some of us were in person, but like some of us didn't feel like confident like meeting up in person to work on the competition together. So like that kind of hindered our communication some like a little bit, because like it's a lot easier to yell across the room than to like communicate over Zoom when like sometimes the Wi-Fi might be a little spotty and stuff like that.
Okay, I think with that, we're about out of time. I just want to say thank you again. It was a really great presentation. And I wanted to remind you that among the hundreds of submissions that we got, we're looking at one of the top 6 teams, which is amazing. And the judges here looked over like the top papers and scoured them, and were highly impressed with your work. And the judges that aren't here gave us their input and wanted to know that you all were among the best of the best. So I could not be more proud, and I'm so excited that you're here with us, and I look forward to seeing you later this afternoon at the award ceremony. Thank you.
Thank you.
Thanks, everyone. Great job.